In this video, we'll go over the answer to question 12 of the 2021 New South Wales HSC Chemistry Exam. This question takes up quite a bit of space in the exam and involves two diagrams, so we will space this out over a couple of slides. Firstly, the question states, the mass spectrum and carbon-13 NMR for an organic compound are shown. This is followed by a plot of a mass spectrum, as seen on this slide, and a plot of carbon-13 NMR spectrum as seen on this slide. Then the question asks, which compound could produce the two spectra? This is then followed by four options showing the expanded structural formula for four organic molecules. Generally, there is no quick way to answer these types of questions. Here we will go through the two spectra and gather clues to the identity of the molecule, eliminating options along the way. Let's start with the mass spectrum. For easy reference, let's also have the four possible options on the right hand side here. The most valuable piece of information in a mass spectrum is usually the very last peak visible. In this case, the mass to charge ratio is 98. This effectively gives us the mass of the entire molecule and tells us we have a molecule of mass 98 atomic mass units. As we can see from the options A through D, we are dealing with a molecule that only has carbon, hydrogen, and oxygen present. Oxygen and carbon are the biggest contributors, so let's start with those. Options A through D all have one oxygen, and so therefore all the molecules are the same at this point. Options A, B, and D have 6 carbons, but option C only has 4. So let's calculate its molecular mass so that we can either find our final answer or eliminate it from the rest of the options. Adding up the contribution from the oxygen, carbon, and hydrogen atoms, our total is 72 mass units, less than the 98. And therefore not the molecule of interest. We can therefore say this option is incorrect. The other options all have the same atom allocation, which adds up to 98 atomic mass units. Therefore, we have gained as much as we can from this spectrum and need to look at the carbon-13 NMR for additional clues or information on the identity of the molecule. As we can see, the NMR spectrum shows 4 peaks, 2 at around 25 parts per million, 1 at around 40 parts per million, and 1 at around 210 parts per million. With 4 peaks, this means we have 4 carbon environments. Let's use the reference data from the back of the exam paper to see if we can identify some of these environments. Firstly, one peak sits far beyond all the others, and that is the one at 210 parts per million. Looking at our reference data, there is only one functional group that has such a high chemical shift, and that is the aldehyde ketone group, usually seen at 190 to 220 parts per million. Therefore, we can already assign this peak to that group. Looking at all the remaining options, A, B, and D, we can see they all contain ketone, so that fits in with the spectrum. Another distinct functional group can be seen on option D, the double bonded carbon. Looking at the reference sheet, we see a molecule with a double bonded carbon should have a peak in the spectrum around 90 to 150 parts per million. However, in this spectrum, we see no such peak. Therefore, we can eliminate option D. This leaves us with two options, options A and B. At this point, we may already see what the answer is, but let's go through each of the carbons and link them with a possible peak on the spectrum. Firstly, we know the carbon with a double bonded oxygen ketone is associated with the peak at 210 parts per million, so let's label this number 1. We will also label the associated peak. Let's assign the next closest carbon environment to this as number 2. For option A, there are 2 identical carbons as the molecule is symmetrical, so we label both as 2. In option B, we will choose the carbon on the right as number 2, and then also the associated peak. The next closest carbon environment we will label as number 3, for both molecules, and then the associated peak. Lastly, carbon number 4 and the peak. We can see that we have now run out of peaks, but option B still has 2 distinct carbon environments to assign. Therefore, option B has a total of 6 carbon environments, 2 more than the spectrum allows, which means we can eliminate that option, and that option A is the correct answer. These references were used in the making of this video. Schell and Hogan have a section on identifying compounds using mass spectra, which covers what we talked about, and also a section on nuclear magnetic resonance, which covers carbon-13 NMR spectra. where we verify that each peak is associated with a single carbon environment. It also includes an example with ethanol. Blackman et al. Also includes a section on carbon-13 spectra and backs up the idea that each peak is associated with only a single carbon environment. If you have any questions or comments, please leave them below. Thanks for watching and see you next time.